Is another example of successive partial differentiation. We have u equivalent to the log, or you can call it the natural logarithm of x squared plus y squared plus z squared, and we've been asked to show that the second derivative of u with respect to x plus the second derivative with respect to y plus the second derivative with respect to z is equivalent to 2 over x squared plus y squared plus z squared or z squared. So in this case, we're going to apply the chain rule in finding the derivative of u with respect to x, since this one is in the form of logarithms. Whenever we are finding the derivative of natural logarithm, or the way you can call it, others call it ln, we are going to say 1 over the inside multiplied by the derivative of the inside. So in this case, we are finding the derivative with respect to x. So let's first write 1 over the inside, which is x squared plus y squared plus z squared, multiplied by the derivative of the inside with respect to x, which means I'm treating y squared and z squared as constants. The derivative of constants is 0, so that means I have the derivative of x squared is 2x plus 0 plus 0. So the reason I have this, I can then rewrite it so that 2x becomes the numerator and this one becomes the denominator. So after that, we have been asked to find the second derivative. So I have to find the second derivative of this. It's a fraction, so we're going to use the quotient rule, which is this one, that is the derivative of u multiplied by v minus u, the derivative of v divided by v squared. Usually u represents the numerator and v represents the denominator in all cases. So our u is going to be 2x and our v is going to be x squared plus y squared plus z squared. We are differentiating with respect to x, so the derivative of 2x will be 2. The derivative of this with respect to x will be 2x dx. So after that, I'm going to replace these values in this quotient rule. That is the derivative of u multiplied by v, that is this by this, so I have 2 multiplied by this one, and then minus u multiplied by derivative of v, that is minus 2 times 2 is 4, x by x is x squared over this. So if I simplify this by opening the brackets, I have 2x squared plus 2y squared plus 2z squared minus 4x squared. This one can then be simplified further, so that we maybe can factor out, let's first calculate this. We have 2x squared and negative 4x squared. My positive 2 minus 4 is going to give us negative 2, sorry. So we're going to rewrite so that the negative 2x squared can come in the inside, so that we don't start our function with negative. So we're going to rewrite it so that we have 2y squared plus 2z squared minus 2x squared. Then after that, I can factorize out 2 because it's common, and we're going to get this as our first, let's call it equation. So that we are going to call that equation 1. And then if we follow the same procedure, so I have this one here. If you follow the same procedure that we have used in calculating the derivative of u with respect to x, you're also going to get identical answers for the derivative of u with respect to y, which is the second derivative of u with respect to y, and the derivative of u with respect to z. So the only thing that is going to change according to our pattern, you're going to notice that in the second derivative of u with respect to x, the value of x was negative. If we derive with respect to y, y will be negative, that is y squared will be negative. That's the only difference. If we find the derivative squared with respect to z, z will have the negative. So you can confirm by working the way we have worked the second derivative of u with respect to x to see if you're going to get this. After that, I'm going to add Roman 1, 2, and 3. So I'm going to have the one where x squared is negative, and this one where y squared is negative, and the one where z squared is negative. I'm then going to open the brackets. First of all, I can factorize out these two because it's all common, so that I can work this directly. So I'll have 2 factorized out. So I'm left with y squared plus z squared minus x squared plus 2x squared plus 2z squared. Positive times negative is negative. Then we have plus, this one is x squared plus y squared. Positive times negative is negative, so we have minus z squared over this. We can then simplify the like terms, like we have y squared minus y squared, that is 0 plus y squared. So we are going to be left with y squared. So if you simplify that, you're going to notice that you're just going to be left with x squared plus y squared plus z squared. And then we can expand our denominator by multiplying this way. So you're going to cancel this with one of these, and you're going to be left with 2 over x squared plus y squared plus z squared. Hence we have proven that the second derivative of y with respect to x plus the second derivative of u with respect to x plus the second derivative of u with respect to y plus the second derivative of u with respect to z is equivalent to this. Thank you so much for watching. Kindly don't forget to like, comment, and subscribe to my channel.